We're going to use a technique called method of partial fraction to integrate x cubed plus x squared plus 2x plus 1 divided by x squared plus 1 times x squared plus 2. First, we have to check that the degree of the numerator, which in this case is 3, is less than the degree of the denominator. Well, the degree of the denominator comes from multiplying x squared by x squared, which is x to the 4th. Therefore, it's 4. So yes, the degree of the numerator is strictly less than the degree of the denominator. Next, notice that x squared plus 1 and x squared plus 2 are both irreducible quadratic polynomials. We cannot break them up and express them as product of two linear terms. So now we can proceed with partial fraction decomposition. We take this rational function, which is fairly complicated, and express it as a sum of less complicated rational functions. So this is the original one. Because our two polynomials in the denominator are quadratic irreducible, the way we'll express it is as follows. A linear polynomial of the type ax plus b will go over the first, x squared plus 1, plus another linear polynomial using different constants. That would be cx plus d goes over the second, which is x squared plus 2. And now multiply by the denominator. We have x cubed plus x squared plus 2x plus 1 equals, after cancellation, ax plus b times x squared plus 2 plus cx plus d times x squared plus 1. There are no constants we can plug in that will help us immediately find any of the four, a, b, c, or d. So this is what we're going to do. We're going to match terms. X cubed plus x squared plus 2x plus 1 equals ax cubed plus 2ax plus bx squared plus 2b plus cx cubed plus cx plus dx squared plus d. And now write this as x cubed plus x squared plus 2x plus 1 equals, the coefficient of x cubed on the right is a plus c. The coefficient of x squared on the right is b plus d. The coefficient of x on the right is 2a plus c. And the constant term on the right is 2b plus d. And we match it with what's on the left. The coefficient of x cubed on the left is 1. That must be a plus c. The coefficient of x squared on the left is also 1. That must be b plus d. The coefficient of x on the left is 2. That must be 2a plus c. The constant term on the left is 1. It must be 2b plus d. So we have four equations with four unknowns. In fact, the first equation and the third involve a and c. The second equation and the fourth involve b and d. And that's what we'll use to solve for all of them. Let's take this third equation, which is 2a plus c equal to 2. And the first one, which is a plus c equals to 1. Subtract this first equation from the third. 2a minus a is a, c minus c is 0, 2 minus 1 is 1, so a must be 1. Plug it back in. A plus c equals 1. That means c must be 0. Now bring in the fourth equation. 2b plus d equals 1. And the second, b plus d equals 1 also. Subtract. 2b minus b is b. These cancel. 1 cancel. b is equal to 0. That means that d must equal to 1. So we solved for a, we solved for b, we solve for c, and we solve for d. Let's return to our integral. Our integral was x cubed plus x squared plus 2x plus 1 divided by x squared plus 1 times x squared plus 2. It is now equal to the integral of ax plus b, so a is 1 and b is 0, so it's just x divided by x squared plus 1 plus cx plus d. C is 0, d is 1, so that's 1 divided by x squared plus 2. And the two integrals on the right are much easier to handle than the integral on the left. Let's go ahead and evaluate these. Here for this one we'll use substitution. U is going to be x squared plus 1. Du will be 2x dx. So 1/2 du is equal to x dx. The integral becomes x dx is just du. So it's 1 divided by u, a half in front, and then du. So it's 1/2 ln of absolute value of u. Since u is x squared plus 1, can never be negative, we can write this as 1/2 times the natural log of x squared plus 1. For the second integral, we're going to use, if you know the formula, you can use it. If you don't, you can use trig substitution. We take square root of 2 and write the substitution as x equal to square root of 2 times tangent theta. So x squared will be 2 times tangent squared of theta. And then x squared plus 2 is going to be 2 tangent squared theta plus 2, which is 2 times tangent squared theta plus 1, and that's equal to 2 times secant squared theta. We then differentiate x, so dx is equal to square root of 2 times secant squared theta d theta. And let's plug that in back into the integral. The integral was 1 divided by x squared plus 2. Using that substitution, the denominator is going to be x squared plus 2, which is now 2 times secant squared theta. The numerator is just dx, which is square root of 2 secant squared theta d theta. As you can see, secant squares cancel. Square root of 2 over 2 is 1 over square root of 2 times the integral of 1 d theta. So this is 1 over square root of 2 times theta. Now what is theta in terms of x? Since the substitution was x equal to the square root of 2 times tangent theta, x divided by square root of 2 is tan theta. And so theta is equal to inverse tangent of x divided by square root of 2. So let's put everything together. Our original integral was x cubed plus x squared plus 2x plus 1 divided by the product of two irreducible quadratic polynomials, x squared plus 1 times x squared plus 2. Using partial fraction decomposition, we wrote that as the integral of x over x squared plus 1 plus 1 over x squared plus 2, the integral of that. And now we evaluated both of these integrals. The first one is 1/2 times the natural log of x squared plus 1. The second one is 1 divided by square root of 2 times inverse tangent of x divided by square root of 2. And now we can add constant of integration at the end. For more videos, visit www.mathprepvideos.com.